Aviation is classified as one of the world's most high-risk industries. Ensuring that a major accident or incident does not occur comes down to the use of technology, training, and regulation. One major piece of technology which assists in the delivery of safe flights around the world is known as TCAS. The Traffic Collision Avoidance System, TCAS, is a well-known system that has been deployed across multiple different aircraft of multiple different aircraft manufacturers since the 1980s. A mid-air collision over the Grand Canyon between two aircraft on the 30th of June 1956 prompted researchers to develop a system which would be able to sense and keep track of other aircraft around an aircraft, and eventually would be able to warn the flight crew when a crash is imminent. After heavy trialing and testing, the first airborne-based TCAS system was certified by the FAA in 1981. TCAS is an airborne-based warning system that does not rely on ground-based air traffic control systems. The use of transponder signals created by different aircraft allows TCAS to detect and track multiple mid-air collision risks. When a conflict is imminent, a prominent traffic sound will fill the cockpit in both affected aircrafts. The system will then tell the flight crew whether to climb or to descend, or to turn left or to turn right to avoid the conflict. The International Civil Aviation Organization now requires that any aircraft that carries more than 19 passengers is to be fitted with TCAS. And if an aircraft has a maximum takeoff weight of more than 5,700 kilograms, it does need to be fitted with TCAS. This presentation will aim to supply the best and most up-to-date information regarding the TCAS system. By the end of this presentation, you will know how the TCAS system works, how to operate said system, the foundations the system was built on, and the importance of the system.
So TCAS, what is it? Well, TCAS stands for Traffic Alert and Collision Avoidance System. It is a navigational system found within many aircraft, including the Airbus A320. It is mandated by ICAO that any aircraft with a maximum takeoff mass of over 5,700 kilograms has to be fitted with such system. Following a series of mid-air collisions, it led to airlines and government agencies seeking to develop an airborne device that can function independently from air traffic control. This device was then to become known as TCAS. The system provides an extra level of protection against mid-air collisions as the device detects and alerts pilots to potential collisions. A basic background of the system is that TCAS is a transponder-based interrogation system capable of displaying conflicting traffic and providing advisory alerts to flight crew. The system consists of antennas, computer processors, and TCAS displays within the cockpit. The antenna continually surveys the airspace around the aircraft and transmits a signal. Any other aircraft with TCAS equipped or with an active transponder will be able to signal reply, enabling detection. TCAS continually monitors and calculates tracked aircraft position, with the system analysing aircraft's attitude, closure rate, and projected flight path in order to predict a penetration. An Airbus A320 and other mandated aircraft can currently be seen to issue two different types of alerts. The A320's current TCAS interface and procedures involve both traffic advisory and revolutionary advisory alerts. A traffic advisory alert is issued when TCAS considers an intruder to be a potential threat. This advisory aims to alert crew to the intruder's position. It does this through an oral message of traffic, as well as the navigational display showcasing amber cues highlighting the intruder's position. It is also important to note that a traffic advisory doesn't specifically require action from the crew. A revolutionary advisory, however, is when TCAS considers an intruder to be a real collision threat. In most cases, TCAS will trigger a traffic advisory alert before revolutionary advisory alert. In the event of a revolutionary alert, an oral message will specify the type of vertical order, for example, such as climb, descent, monitor, and adjust. The alert will also specify red cues on the navigational display in which highlights the intruder in conjunction with green and red zones on the vertical speed indicator specifying type of maneuver the pilot needs to perform. Here is an example of a traffic advisory and revolutionary advisory alert.
Traffic. Descend. Climb now. Clear of conflict.
Hello, my name is William Gardner, and in this section of the presentation I will provide details regarding the technology TCAS utilized at inception and how the system operates today. To do this, I will introduce the foundation technology that led to the development of TCAS, as well as an analysis of the various components the system utilizes. This will then be followed by an overview of the different classes and use cases for the system, both when it was first introduced and how it is categorized in the present day. The first concepts for the modern system of TCAS originated in the mid-1970s under the label Beacon-Based Collision Avoidance System, or BCAS. These concepts arose from a desire to have aircraft-based collision avoidance for areas where there was limited air traffic control services. In particular, for such situations where ATC could not provide surveillance-based separation. As described in the 1970 report by Schumann, BCAS was to be an active system consisting of an airborne interrogator used omnidirectionally to transmit altitude. Replies are received from an aircraft within approximately 20 miles, providing that those aircraft are also equipped with air traffic control radar beacon system and reporting altimeters. The system then processes the range and altitude of the responding aircraft, building a track to evaluate whether or not such aircraft pose a threat of collision. If the system does determine that there is a time to collision within 30 seconds, then such warning is displayed to the pilot. These early systems provided the foundation for the technological and computational requirements that would lead to the development and progression made by TCAS. Such a system was revolutionary for its time and paved the way for the smarter and safer aircraft to come. As discussed, the early concepts for BCAS provided the foundation for what would become known as the Traffic Collision Avoidance System, or TCAS. Early in conceptual development, it became obvious that the system will require different levels of guidance and therefore different categorization. The first of these classes is TCAS 1. This version is limited in that it does not contain the ability to provide the pilot with directions for how the pilot should maneuver their aircraft. The class is derived from the early concepts of BCAS, which relied on pilots maintaining outside situational awareness to determine appropriate action. The primary use case is for smaller aircraft, which fly at far slower speeds and do not require such a large surveillance range. This allows for a reduction in cost for the system, making it more accessible for the general aviation and light commercial market it was intended for. The specification for TCAS 2 was also derived very heavily from the founding technology in BCAS. It was intended for larger aircraft and can provide pilots with traffic advisories for a far greater range than TCAS 1. As introduced earlier, BCAS relied on the use of similar technology and was intended to be computationally advanced enough to provide pilots with advisories for evasive maneuvering. With TCAS 2, this is done in the vertical plane only, as it is the most reliable way to ensure that a mid-air collision is avoided. TCAS 3 was a design specification intended to be developed and implemented as the next level of progression from TCAS 2. It would utilize the technology standards seen in the previous classes and build upon the maneuvering information relayed to the pilots. It would provide horizontal advisories in addition to the vertical ones that TCAS 2 utilizes. However, this required for far more accurate surveillance of the surrounding aircraft to operate as safely. Whilst the transmission and receiving of aircraft altimeter data was easily achieved with TCAS 2, and would quickly and accurately provide the information necessary for avoidance, laterally was far more difficult. This was evident in the 1989 journal article by William H. Harmon, where he describes the difficulties associated with accurate horizontal tracking. Any number of surveillance error and subsequent incorrect pilot advisory would make a situation extremely dangerous. His program developed a monopulse antenna with the goal of having it sufficiently sized and well placed enough to provide the accuracy required to use horizontal collision avoidance methods. Due to the complexity of development for TCAS 3, the industry today has settled on the widespread implementation of TCAS 2. This conclusion has been drawn as a balance between the flexibility in maneuvering options and the safety levels required of the system. The following section of this presentation will seek to outline the core components in TCAS 2 and how they link together. The first of these components is categorized as the TCAS computer unit. This provides the computational power to monitor the aircraft's own position and track in addition to the data received from surrounding aircraft. It then uses this information to plot aircraft tracks and assess the risk for possible collision. The unit will then assess the parameters for an avoidance maneuver and determine an adequate vertical miss distance. If the threat aircraft is also equipped with a functional TCAS 2 system, then the two will coordinate their vertical avoidance maneuvers. The Mode S transponder is essential for the operation of TCAS. Not only is it used by other aircraft when transmitting normal functions for ground-based air traffic control, but it is also used to provide a means to communicate between aircraft TCAS systems. This is what allows for the coordination for the avoidance maneuvers and is a vital component for the safe operation of the system. The TCAS 2 system utilizes a variety of antennas on the aircraft, with the purpose of having both increased detection range as well as built-in redundancy. The first is a directional antenna mounted on top of the aircraft. This is paired with an omnidirectional antenna on the underside of the fuselage, which operates at both reduced power and transmission rate. However, both of these transmit interrogations at 1030 MHz. The information processed by the TCAS computer is presented to the pilots via the traffic display. This instrument can be used to give pilots a visual representation of the surrounding aircraft. It can be set to either display full-time or to only activate when the TCAS computer signals either a traffic advisory or a resolution advisory. The figure shown on the slide depicts the standardized symbols used to inform the pilot of aircraft and the danger that they may pose. Cockpit presentation refers to the multitude of ways that the TCAS system interfaces with pilots. Arguably the most useful of these is the resolution advisory displaying the recommended vertical speed to avoid a threat aircraft. This is shown in the figure included, where the TCAS is displaying the threatening aircraft as well as the required vertical speed to assure that the aircraft can avoid a potential collision by a sufficient margin.
The TCAS system, the system which revolutionized safety in air collision in the aviation industry. Let's begin. So basically, I'll be talking about the significance of the system, the importance of why it was implemented. So I'll get into it. It can be said in the early days, the pilots were the collision system. They were and always have been the first and foremost collision avoidance systems. As the pilots became and capable of flying blind instruments by the 1930s, the air traffic control, due to the demand, required for coordination to be increased, which required more safety. In the early days of commercial aviation, air traffic was only controlled procedurally through communications between the pilots through radio reports and pilots verifying their position, which in the end means that the airspace wasn't controlled safely at all, and which led to my next point, a mid-air collision. Due to all the unreliability and safety hazards of the points mentioned beforehand, there was an occurrence of a mid-air collision occurred in 1956, which occurred over the Grand Canyon, and due to the severity of this incident, the safety authorities didn't take any more chances, and they started to develop airborne collision systems. And fast forward 30 years later, we have the invention of the TCAS system. So, the function of the system. How does it work? Basically, TCAS is a family of airborne devices that function independently through ground-based air traffic control, also known as ATC, and that system basically provides all the collision avoidance protection, and it provides them for basically all aircraft types, which makes it very reliable. All the TCAS systems provide some degree of collision and alert to airborne threats. Some of the key components which help the system operate safely and efficiently include the TCAS computer unit, the Mode S transponder, and the TCAS control panel. The TCAS computer unit. Basically, the TCAS computer unit looks something like this, according to the picture in the PowerPoint. It basically is the computer unit is also known as the TCAS processor, and it's known to perform aircraft surveillance, which include intruder tracking, the aircraft tracking for the plane they're flying in, or many forms of threat detection, RA maneuver determination and selection, and many more advisories, including that. The TCAS processor also uses pressure altitude, radar altitude, and all other discrete status inputs from their own aircraft to controlling the collision avoidance system parameters involved. If a tracked aircraft selects an avoidance maneuver, that aircraft will provide adequate vertical miss distance from the intruder, and which generally leads to the minimization of an air collision occurring. And it also does all that while generally minimizing any changes to the original flight path set. Now moving on to the Mode S transponder. So basically, the Mode S transponder looks something like this, as shown in the image there. It's basically the most important part of the TCAS system, and that's basically how it operates. So what the transponder consists of 4 typical control panel positions. Basically, has a standby, a full transponder mode, a TA, which stands for traffic advisory, and a automatic traffic advisory or a resolution advisory mode. So basically, what it does is basically allows the flight crew to select and control all TCAS modes. So now I'll explain each mode and how it works. So basically you have the standby mode in that case, which basically means the power is applied to the TCAS processor and the transponder, but TCAS does not issue any interrogations, and the transponder will only rely to discrete interrogations. And basically that means that the transponder will still transmit all its squitters and stuff. And now move on to transponder mode. So basically it's just a normal transponder mode. Basically it means that the transponder is fully operational and will reply to all appropriate ground and TCAS interrogations. But in this case the TCAS does remain in standby, so that's something to be wary of. The next mode is the traffic advisory mode, so that's also short form for TA. In this case also the transponder is fully operational. TCAS will operate normally and issue appropriate interrogations and all tracking functions however necessary. And it is also important to consider in this mode the TCAS will only issue the traffic advisories and the RAs. In this case it will be all inhibited, so that's something to be noted of. And finally you have the final mode, which is just the automatic traffic advisory and resolution mode. In this case it also means the transponder is fully operational. TCAS will operate all normally and all appropriate interrogations and tracking will occur. So basically the TCAS control panel, it consists of two flight displays. It is the traffic advisory display, as can be seen, and the resolution display. I'll just give a brief explanation on what they do and how they operate. So basically the traffic display on the right, as can be seen in the image, it can be implemented on an either part-time or full-time basis, and it depicts the position of nearby aircraft relevant to the aircraft you're flying in. It also displays some basic traffic information, which include the vertical speeds, the approximate TA and RA statuses. So basically the primary function, the key function which of the display is to basically aid the flight crew to visual acquisition of the transponder. So basically in worst case scenario help them avoid a mid-air collision. The RA display, the resolution display, it provides the pilot with information on the vertical speed, the pitch angle to fly to avoid an encounter. It is also implemented on a vertical speed indicator and also part of a vertical speed tape that is part of the primary flight display, which uses pitch cues, which is also displayed on the primary flight display. The guidance has also been implemented in the head-up display, and basically means the implementations are using the 1415 VSI on the vertical speed tape, which basically utilizes the red and green light markings, which can be seen in the image on the right hand side. So basically what the green and red mean is the red means the vertical speed to basically avoid, and the green basically means the vertical speed to be flown in. And basically, sum it all up, it uses pitch cues also. It uses the PFD to show the pitch angles to be flown to and to pitch angles to avoid in the worst case scenario, and also uses a unique shape to indicate the flight path to be flown or avoided in a worst encounter.
TCAS is well known on the A320 system as being easy to use and mostly automated. The Airbus's A320's traffic alert and collision avoidance system is able to detect any aircraft flying within a 100 nautical mile range that is equipped with transponders. Display predicted air collision risks and can issue verbal orders to the flight crew to descend or ascend to avoid conflict. The system comprises of a single mode switch and is integrated with a small ATC panel on the Airbus A320 aircraft. A single channel TCAS computer, 2 antennas, and 2 Mode S ATC transponders, one standby and one active, are also included in the TCAS system. The A320's TCAS systems have 2 modes of operation. These modes are TA/RA and just TA. TA/RA is the standard mode of operation for the TCAS system. This allows the display and notification of all possible conflicts. TA only notify the aircraft if in extreme circumstances. This mode is normally used when the aircraft is over parallel runways, in degraded performance conditions, engine failure, or when the landing gear is extended. If the TCAS system is in automatic mode, TA mode will automatically activate under 1000 feet AGL. Lastly, if the aircraft is below 500 feet, all TCAS systems are not shown. The TCAS is operated by 2 switches on the ATC control panel. This is shown in the figure on the slide. Switch number 1 is the mode selector, and switch number 2 is the traffic selector switch. It allows the flight crew to select whether TA or RA warnings to receive. When the system is deactivated, in standby mode, the transponder still emits a frequency so that any aircraft around the current aircraft can still receive warnings. This is done as a fail-safe, protecting other aircraft that may be in the vicinity. The 8th most closest and threatening collision risks are only shown on the glass nav instrument at one time. As shown in the figure on this slide, no risk aircraft are shown as a white diamond, TA risks are shown as an amber circle, and an RA risk is shown as a red square. All these assist flight crews in ensuring once a TCAS is triggered, that the safest course of action can be taken to mitigate the risk of the collision. As soon as a TA or RA alert is issued to the flight crew, the words traffic will be sounded in the cockpit. Shortly after, the system will tell the crew to descend or to climb. This will be reflected on the vertical speed indicator as the green zone, as seen in the diagram on this slide. As soon as the aircraft is safe, a clear of conflict notification will be sounded. Other audio messages given by the TCAS is also shown on the list on this slide. Finally, on the next slide shows a short 30-second video of a Swiss Airbus receiving a TCAS warning. Take note on how the flight crew react to this threat. Thank you.
Traffic.
Traffic, TCAS, you have control.
Yeah, I have control, TCAS.
Climbing with a high rate, das ist jetzt schon gut.
Speed 1000, station below.
2219, reduce speed to 210. 210, break climb 1090. Air 1639, approach 133.05. 3305, break 1639.
Ja, ist clear of conflict.
Yeah.
In conclusion, this presentation has provided the best and most up-to-date information regarding the Airbus A320's TCAS system. The report has provided in detail through investigation, analysis and targeted research a clear understanding to how the TCAS system works, how to operate said system, the foundations the system was built on, and the importance of the system. The air transport industry, along with technology, is forever changing and evolving, with systems constantly being upgraded, implemented, and advanced. Therefore, further investigation and research would be essential for any future investigation. Recommendations for a future study would include TCAS implementation for other aircraft, training surrounding TCAS, and addressing limitations to our presentation. Undoubtedly, it is clear that TCAS is a major piece of technology that assists with the delivery of safe flights, and that with the continued implementation of the technology, training, and regulation surrounding TCAS, that the likelihood of a major mid-air collision doesn't occur. Once again, thanks again for listening to Angad, Mitchell, Williams, and myself's presentation on the A320 TCAS system.